Yes, there is a midterm. Yep, it is on March 5th. No, I'm glad you bring this up because I did mention this at the very beginning. The midterm will be very much like homework out of the book. So it's just going to be very, find the equation of the plane or the line of the intersection of two planes. So it's very much mechanical stuff that if you've done the take-homes, then finding the equation of a line of intersection of two planes should be pretty trivial. Yep. Mm-hmm. I don't know. What I do know is that the mini exams that I do give you, no one that I teach with does that. I mean, these are exams that I've made that I think challenge you to an appropriate level. Because, I mean, some of the material in Calculus 3 is pretty clear. I mean, it's just not, I could ask you a test of, hey, let's find the cross product of two vectors. Really? I mean, really? That's not Cal 3, Yeah. Well, I'm sorry if you expected it to be a little easier. That's why I keep asking you, Okay. I want you to be challenged. I mean, but not impossible. I'm not trying to set an impossible hurdle for you to cross. I've taught this way a few times. I've taught this class over the last couple. Guys, please. Okay. I've taught this way a few times, and every class I've had a lot of success with it. The take-home exam model that I do in this class is very much like what you'll find in a university setting when you're in higher level courses. Almost all of it's take-home, and it's a lot of work. So I'm just trying to gear you that way. And if I had done this in the past and I had like 3 people pass, I wouldn't feel good about it. But I've had, class start with 18, 19, 20 people like this and have 12 students get through all A's. I mean, usually if you get through this first couple of mini exams, you are going to most likely get an A in this class because you know now what's expected, and you just keep going. It's going to be a long road, but I mean, you'll get through it, and at the end, you'll get the grade you deserve. So I don't know if that answers your question. It's a lot of work. I know what I'm asking of you. Okay, we ended last time with 11.2, and we had started talking about limits, and we were very much disturbed with the idea that we cannot always approach. Was this the one? Yeah, we did. We skipped. Yeah, this one didn't exist. So I think what I'll do is I'll start with this one, 11.2.7. So the idea, again, was three-dimensionally. You're trying to approach this point. There's infinite number of paths. How do you check all the paths, right? That's where we were. So here's an example. Let's investigate this. Everyone has their notes, right? This limit, x approaches 0, 0, xy approaches 0, 0 of xy squared over x squared plus y to the fourth along several paths leading to 0, 0. So the first thing we do is we go along the y-axis. Okay, so the picture of this, y'all remember this? I mean, it wasn't that long ago, right? We go along the y-axis, and what it looks like happening is that we're at 0. But let's do this algebraically now. Let's make sure we can back up what we're seeing with what's happening algebraically. So what I want to do is go in along the x-axis, which means that y is 0, right? So what do we do then? Replace all the y's with 0 in the limit, right? In the function inside. So replace all your y's with 0. You get limit xy goes to 0, 0 of x y squared over x squared. Oh, I forgot to put in the 0, didn't I? x, and then here's 0 squared, and then x squared plus 0 squared. So what does that equal to? 0, because you have 0 on top, right? You have 0 on top over x squared, and that is equal to 0. You do not take the limit now, right? 0 divided by x is going to be 0 as long as x isn't 0. So you always turn it into 0 before you try the limit. So that's 0, right? Pretty straightforward. So coming in along the x-axis, it's 0. Now let's go in along the y-axis. Get out of here. Okay, along the x-axis here. So if we go along the x-axis or y-axis, we are going to let what be what? X be 0. And this is pretty clean, straightforward too, isn't it? Limit xy goes to 0, 0. The numerator becomes 0. Denominator becomes what? Y to the 4th, right? So again, we get 0. And so 0. So that matches what happens. So coming along the x-axis or y-axis, it's going to 0. We're happy until we get to the next one we're going to try. And I don't think we did this last class. We're going to come in along along the line y equals mx. Now this means we're coming in along any line that passes through the origin. Look, this is a top view of our surface. What we're going to try and do is come in along any line approaching 0, 0. And would you agree that any line that goes through the origin has the equation y equals mx? Y equals mx? Not plus b, because what's b? 0, because b is the y-intercept. So what would happen if I try and come in along any line at all? Let's see. Try and get this. Give myself a little more room. All right. Here's what we would have. Limit xy approaches 0, 0 of, now what am I replacing with what? Y is going to be replaced with mx, right? So I will have in the numerator x, then times mx squared over x squared plus mx to the 4th, which is x cubed m squared over x squared plus m 4th x to the 4th. So just replacing all your y's with mx, raising them to the appropriate powers. What can I factor out of the top? I wanted to cancel with some stuff in the bottom, so how about just x squared? If I factor out x squared, I have m squared, right, over, or sorry, xm squared over 1 plus m to the 4th x squared. So I factored an x squared out of everything and canceled. And now what happens if you let x go to 0? Let x go to 0 right now. This whole top goes to 0, right? There's no y, right? So I don't have to let y go to 0. Then if x goes 0, that whole thing goes 0. So what you get is 0 over 1, and that's 0, right? We don't have 0 over 0. We have 0 over 1, and that's 0. So that tells us that if we try and approach the origin through any line headed to the origin, we're coming in at 0, or coming in towards 0. Yes or no? Yes? If we're headed towards the origin from any line, then we are going to be, our function's value is headed towards 0. There was the line, any line. Top view, we come in along any line towards the origin, we're headed towards 0. So that leads us to believe that possibly, maybe we're lucky in that any way we come into the origin, it's always 0. So then we try something else, and this is where things aren't going to be good. So that's what I said. We think it's good, but now let's try it along the curve x equals y squared. And I showed you this last class. When we do that, we actually come in along this parabola. Do y'all see that? And that's higher than most of the other part of the surface, and so it's not headed towards 0. But let's show it algebraically. Now, someone might ask, why would you know? Bless you. Why would you know to choose that, right? And that is a challenge. I can't answer that question. I don't know how you would know. You would just have to investigate the inside of the limit and start thinking, like, what can I try to make it something other than 0? So I want to go rewrite, replacing my x with y squared, right? So what do I get on top? If x becomes y squared, y to the 4th, bottom, it's y to the 4th plus y to the 4th, right? 2y to the 4th, which is 1/2. Which is not 0, right? That's not 0. And therefore, the limit does not exist. Because I found a path that headed towards the origin that the limit was something other than 0. How do I know that this path heads towards the origin? I mean, everyone, the x-axis and y-axis head towards the origin, right? Any line mx, y equals mx, headed through the origin? Why does this head through the origin? What does that curve look like? If this is x and this is y. It's like that, right? Does it contain the origin? 0, 0 satisfies the equation? So, I mean, you couldn't just pick anything. Whatever you pick, whatever curve you pick, it would have to go through the origin, where you're headed. All right, questions? Yeah, but it's not. What we're going to do, like on the homework, is that you're going to start picking different paths. You'll always start x-axis, then y-axis, then maybe try y equals mx. And you're hoping to get different limits. Now, if x-axis, y-axis, and mx don't work, then you're going to have to try something else. And that's where you have to just be creative. And I gave you an example of something like that. See if you can try that yourself and try something. So yeah, guess and check would kind of be what you would employ there. But then there's, whoa, I hit the wrong one. There's also, so that limit didn't exist, but there's also what's called the Squeeze Theorem that can help us find limits. Now this is taken from Cal 1. We use Squeeze Theorem in Cal 1. You actually used it to show several different limits. All the Squeeze Theorem says is that if you have a function of two variables, which we'll call f of x, y, and it is always stuck between two other functions of x and y, as long as your x and y are near some point. So that means in some little area, this inequality is true. Then if this one right here, this limit has to be less than that limit, has to be less than that limit. So the inequalities must hold when you take the limit. So what we try to do in the Squeeze Theorem is we try and get these outer two to do what? Go to 0 or go to the same place. If the outer two limits go to the same place, the middle limit must be squeezed between and go to the same place also. But they have to be the same place. Here's an example. I'm not going to go through the process of trying to come in the x-axis and the y-axis and y equals. I'm not going to do that because it actually turns out that this one, the limit does exist. So you would never be able to show it by trying paths. You would have to use Squeeze Theorem. So here I go. I need to try and convince you that I can cram that inside. I can do this right here. I can get that, and I can put it between two functions that when I take the limit as I go to 0, 0, because that's the point here, that I can make the outsides go to the same place and squeeze that piece in between. So let's see if I can convince you of this. First thing, do you agree that sine squared y times, times x squared over x squared plus 2y squared. Do you agree that that's less than sine squared y and greater than or equal to 0? Do you agree with that? So let's talk about it. That's the stuff that's not sine squared y, right? What's x squared divided by x squared itself? 1, right? So if I say x squared divided by x squared plus 2y squared, isn't 2y squared guaranteed to be some positive number? Yes? So x squared plus 2y squared is bigger than x squared. So x squared divided by something bigger than x squared should be smaller than what? This should be less than or equal to 1, shouldn't it? Anything divided by itself is 1, but anything divided by itself plus something bigger would make that less than 1. Do y'all agree? How do I know that everything here in the middle is bigger than 0? Sine squared has got to be bigger than 0, right? X squared has got to be bigger than 0. I mean, it could be 0, right? But then the equality holds. So the numerator's got to be a positive number. Denominator, same thing, right? You're adding two positive numbers together. So if the part in like the yellowish orange is less than 1, then if I put that 1 in front of this sine squared, then do you see how this is bigger than this? Because that is 1 times sine squared. This is a number smaller than 1 times sine squared. You all see it? This is 1 in front of sine squared y. This right here is a number smaller than 1 in front of sine squared y. So therefore, it's got to be smaller than the sine squared y. Now, if you believe that, if you agree with that, then right now, if I take the limit, I take this and I say, what's the limit as xy approaches 0, 0 of 0? And then on this side, bring it down a little more. What's the limit as xy approaches 0, 0 of sine squared y? This is obviously what? Left side? 0. And the right side, well, the only thing you have to be concerned about is the y variable. And what's sine of 0? 0. 0 squared, 0. So the right side also goes to 0. So if the left side, the limit goes to 0, and the right side, the limit goes to 0, that forces your inside to also go to 0. So therefore, this is equal to 0. And you never have to test any paths. What's the hardest part of this problem? Exactly. Finding what to have your outside functions. What are you going to use? And every problem is unique. So you'll have to just look at it, play with it, try different things. Just remember that when you set up this inequality, you better know what happens to this one. Like this the one on the right better be something you know what happens when you take that limit. If the one on the right you don't know what happens, then you won't be able to squeeze because you won't know where it goes. All right. Let me copy. So I want to show you kind of what I mean by that real quick. What if I had done this? You tell me if this would have been right first, and then let's talk about what it would have been. What if I would have tried this instead? Would that have been true? Is this smaller than this? Well, the x squared over x squared plus 2y squared, that's exactly the same, right? So the only question is, what about sine squared y? Sine squared y is between what? 0 and 1, right? So the biggest it could ever be is 1. If it's 1, then it matches the right side, doesn't it? If it's smaller, then hell, it's smaller, isn't it? So that inequality is actually true. But what's wrong with it? Take your limit as x, y go to 0, 0. And what do you get on the right side? Let x and y go to 0, 0, 0. What do you get? 0 over 0, indeterminate form. You can't figure out that answer. But you can't apply L'Hopital's rule to functions of two variables. That only works functions of one variable. Right? Because when you take the derivative, then how would you take the derivative of the y part? Like derivative top, you might say 2x. Bottom, 2x plus, then what's the derivative of 2y squared? Is it 4y? You know what I'm saying? It's kind of tricky. So, all right. So this would not have worked. Moral of the story. That would have been a bad choice. Make sense? Okay. All right. Moving along. Where are we here? Continuity. So continuity just has to do with a function that, remember, continuous in Cal 1 meant your curve goes to the same place, and wherever it's going to, it's got a solid hole there. I mean, a solid hole, solid dot. It's going to a place. It doesn't have a hole in there. No jump. So continuity for functions of several variables is the same thing. It's a surface. It doesn't have a hole in it. Or remember we saw some of those surfaces that looked like they were weird. They like did something crazy like this, right? We saw those last time. Continuity just means that it's nice, like a sheet, like a blanket blowing in the wind. Everything's nice and connected and smooth. Well, that's the definition of it. For us, we just want to remember that all polynomial functions of two variables are continuous everywhere. Rational functions are continuous on their implied domains. Implied domains means anywhere where you don't have division by 0 or square roots of negative numbers, things like that. And then composition of continuous functions are continuous on their implied domains. So that's just a little thing we need to remember as we move forward. And there's the homework out of that section. 5 through 13 odd. All right, we're out of 11.2. We're going to start 11.3 today. Partial derivatives. Now things start to get a little interesting. Okay, remember from Cal 1 that when we had a function of one variable, we had this point that we called x naught. That's x with a little 0 subscript. X naught, if we wanted to find the derivative of the function at a point, then that derivative represented the slope of the tangent line, correct? So we pick some point find the slope of the tangent line of the function there. The red number there represents what there? Negative 16.5 represents what? Slope of that line, the pitch of that line, right? The problem that we encounter with functions of several variables is that if we have two variables, it makes it very difficult for us to determine a single tangent line. So let's take a look at this. I love this demo. Let's see if I can make it a little bigger. I don't know. Let me first get that point over to somewhere where we can kind of see it. All right, do you all see that point? Do you see where it kind of lives here? Okay, that's my 3D. Uh-oh. I might have just lost it. No, looks like it's still going. Okay, I won't spin it around anymore. I'm going to turn the lights down a little bit for this demo. Way down. Okay, so if I'm trying to find the slope of the tangent line of a surface, it becomes very challenging because where is it? I mean, what line are we talking about, right? If you have a curve two-dimensionally, there's one point, there's only one line that makes sense, right? Here there's, do you see that? I mean, how do you even talk about it? Yay or nay? So how about this? How about I imagine that I slice my graph with a plane, and that plane is parallel to the xz axis. So this is, if a line is parallel to the xz axis, it has the equation y equals a constant, right? Planes parallel to the xz axis are y equals a constant. So what I've done here is I've held my y as a constant. If I do that, the intersection of the surface with that plane is that green curve, right? That's what it is. So if I come in here and I look at it from way out the y-axis, it would look like that. Now I can draw back the surface and kind of pull the surface, all that other crap, completely out of the picture. And now I'm looking at it just from the side where that plane came in, right? And if I look at it that way, that's a Cal 1 problem, isn't it? And I should have a tangent line there. Do you agree? Yes. Here it is. I'm going to come back. See it right there? I'm going to bring the surface back in. We're talking about that. Okay? That's a Cal 1 problem. If I hold my y constant, then it's just that black line is the line I'm talking about. Now I can change my x value. If I change my x value, I'm just going to be at a different point on that green curve. Yes? Just moving along and that black tangent line changes. Now that's if I chose to hold my y constant. What if I had instead decided to hold my x constant? Then my plane would come in the other direction, right? Like this, parallel to the YZ plane. And now if I look at that, it should have a tangent line. Uh-oh. Oh, it didn't like that. Bring my opacity back down. For some reason, it's not liking that. I'm afraid to do it now. Oh, there we go. There we go. I was clicking the wrong thing, wasn't I? Show partial y. So, see the red one? Yes? Okay, now I'm going to bring the other one back in. If we fix x and y, they gave us those two lines, didn't they? We have the black one and we have the red one. And together, what would those, if I have two lines, what do two lines make in space? Two lines together, you have a plane through those two lines, don't you? So we actually get this concept of a tangent plane, which we'll get to. Right now what we're saying, though, is in order for us to talk about a derivative of a function of two variables, we're going to have to attack it one piece at a time. First, we'll have to hold the y constant so we can get a derivative in one direction, and then we'll hold the x constant to get the derivative in the other direction. Make sense? Any questions on this picture? Now I have this coded up here so that you can do different surfaces. That was the surface sine x minus y plus cosine x. Let me do this one here. Look at this one. This is like a saddle. You go in here, you cut it one way, parabola, right? Cut it the other way, parabola the other direction. Here's the tangents. Let me get the surface out of there. See? That makes sense, picture-wise? All right, we're going to proceed. I'm changing right now the x value, which changes the slope of the black line, right? If I change the y value, it'll change the slope of the red one, but the black one stays the same the whole time. All right, the key, to find a derivative at some point, we will need to either hold x or y constant. That's the key to this whole thing. So given z equals f of x, y, if we hold y constant, we call the derivative the partial derivative with respect to x. So this is a language thing. We now have this idea of what's called a partial derivative. If I say partial derivative with respect to x, that means you're holding your y constant. And this is the notation. We don't use a little prime mark anymore. We do our f, and we do a subscript x and then xy. That's the derivative, the partial derivative with respect to x. Now, if we hold the x constant, we call it the partial derivative with respect to y, and we put a little y down there instead. By the way, what's the derivative of a constant? 0, right? Derivative of constant 0? So let's do this problem here. Maybe you're thinking partial fractions. Yeah. No. This is the derivative you learned in Calculus 1, except we're trying to do it on a function that has both x's and y's in it. So what we need to do is we need to figure out how to do it. The way we do it is if we want to find the derivative on a surface, we have to hold one of the variables constant, differentiate with respect to the other variable, and then do the other one also. Yes? Oh yeah, we can do lights back, sorry. So let's see what this is asking. Part A says find f subscript x 2, 1. That means the partial derivative with respect to x at 2, 1, the point 2, 1. So somewhere on the surface there's a point. They want us to cut through it with this plane, right? Which is parallel to the, if I'm doing it with respect to x, I'm holding what constant? Y. So if it's y, then that means it's parallel to the xz plane. I'm cutting through the surface with this plane, and it creates a curve. And at the point 2, 1, I want to know the slope of the tangent line. Yes? Do you think you would understand that if I hadn't shown you the picture? It'd be probably a little more difficult, right? We're going to hold y constant. There's a plane cutting through. I mean, that wouldn't make as much sense, right? Okay. But visually, I think hopefully you're okay with it. So first thing I'm going to do is this. I'm going to first find what's the partial with respect to x of the function. And then later, I'll plug in 2, 1. Just like we do with normal derivatives in Cal 1. You want to know slope at a certain point? First, you find the derivative, then you plug in the x value. Here, we're going to find derivative and then plug in the x and y value. So what is the partial? All right, let's look at this. Y cubed is our first term. What's derivative of y cubed? 0. Why? Because y is a constant, right? So that may as well be 5 cubed. Any number, doesn't matter. But it's 0 because it's just a number. Okay, what's the derivative of the next term, 2x? 2. Okay, what's the derivative of the next term? Well, what's y to the fifth? Well, no, not what's the derivative. What is y to the fifth? It's a constant, right? So you're going to bring it down with you, right? That's like a constant in front of x squared. I'm going to give you an example next to this. Isn't this 10x squared? Isn't that a constant in front of x squared? And the derivative of that would be what, 20x? Well, what we have here is our y to the fifth is like the 10. It's a constant, so it's just going to come down, and then we need derivative of x squared, which is 2x. So we have the 2, we have the y to the fifth, and we have the x. So it should be 2y to the fifth times x, or 2x y to the fifth. You understand that? Plus 0, because the derivative of 10 is 0. That is the derivative, partial derivative of f with respect to x. Now let's try this. Can I erase? I never put the final answer, but you realize the zeros are just gone and then you're done, right? Yeah, we need to plug in. Let me do that. I don't want to leave us without the final answer. At partial derivative of f with respect to x at 2, 1 is equal to, plugging in 2 for x and 1 for y, we get 2 plus 2 times 1 to the fifth, which is what? 6. So wherever that plane cuts through, take the slope tangent line, it's 6. Now I'll take a picture. All right, next one. What I'm going to do now is I'm going to do the partial derivative of f with respect to y. And now I'm going to treat what like what? X is a constant. So then what is the derivative of y cubed? 3y squared. And what is the derivative of 2x? 0, because x is a constant. That may as well be 2 times 5, which is 10. Derivative of 10 is 0. And then what's the derivative of x squared y to the fifth? 5y to the fourth, and then the x squared is our constant, so it just comes down with it. So how about I put 5, I'm going to just put them in the order we normally do. 5x squared y to the fourth. And the derivative of 10? 0. So now what's partial derivative of f with respect to y at 2, 1? 3 times 1 squared plus 5 times 2 squared times 1 to the fourth. 3 plus 20? 23. We good? I'm going to get back to Luke's question. I guess Cal 3 isn't that bad, but I make it bad, huh? If you just had to do this all day. It actually does get a little harder. I mean, outside of my mini exams, it does get a little harder. All right, let's keep moving. It's going to be kind of testing your differentiation skills now. Let's try and find f, partial of f, with respect to x. All right, so you have sine, and inside you have xy over x squared plus y squared. So what do you think you're going to have to use here in order to take that derivative? Chain rule. What's derivative of sine of something? Cosine of the something, right? Cosine of the something. Now you have to take derivative of what's inside, right? That's something. And inside is quotient, which means you need to apply the quotient rule. So the quotient rule, I'm going to just start preparing for it over here. It's like, what? Derivative of the top one times the bottom minus derivative of the bottom times the top all over the bottom squared, however you remember quotient rule. Yes, I've heard that before also. So whichever way you like it. How many of you learned the low D high, high D low? Yes? So you want to do it that way? Low D high means the low one, the bottom, times D high means derivative of the top. So let's write that down. That's the top left corner, right? So I have x squared plus y squared. And then what's the derivative of the top? What's D high? What's the derivative of xy? We're treating y like a constant, right? So that may as well say 5x up top. What's the derivative of 5x? 5. So what's the derivative of yx? Y. The tricky part is just keeping track of what's your constant, what's not. Okay, minus, that was high D low. Or no, that was low D high. Now high D low. High is xy times D low. What's the derivative of the bottom with respect to x holding y as a constant? 2x. 2x and then what? That's it? Oh no, okay, yeah, but on the top, this derivative was just 2x, right? In here, top right. The derivative of the bottom is just 2x because y squared is a constant. Derivative constant is 0. All over now the bottom squared. And then you start cleaning it up and stuff, and I'm not going to do any of that. Let's see if you can do this one now. Partial with respect to y. So if we have this, we can go cosine again, xy over x squared plus y squared. But now we're holding x constant. So quotient rule again. What's the derivative of the top with respect to y? Just x, right? I'm going to write mine a little different than last time. I'm not using the low D high, high D low. I'm just doing it. Derivative of top times the bottom minus derivative of the bottom. What's the derivative of the bottom with respect to y? 2y times the top all over the bottom squared. Are they the same? Are those answers the same? They don't look the same, do they? If you expand everything out, don't believe they're going to give you the same answer. So, got it? This is very mechanical. Just take derivative. Now, just like in Cal 1, we have different notations for taking the first derivative. All of these notations are the same, and I'll use them. You know, I'll kind of choose what I want when I want, but you should just be familiar with all these. Whenever you see TFAE, that means the following are equivalent. So this is the first one we saw. The second one is kind of like if you just wrote f prime. It's real short. F, take derivative of f with respect to x. This one right here, these little symbols here are kind of like your differential back in Cal 1. Remember you had this? You had dy dx. Well, these are not, they're not the same d. It's a del. So it's kind of curvy looking. It's like a backwards 6 almost. Okay? That means partial derivative of y with respect to x. Or in this case, partial of f with respect to y. That's the same as this. Remember, z is equal to f of x, y. Partial of z with respect to x, or partial with respect to x of f of x, y. Or these are nice. F with the 1 underneath it means the partial with respect to x. Capital D, 1, then f means partial derivative with respect to x. And then this one, d, capital D with little x and f. There's lots of different notations, right? Just be aware that they're out there. And if you have a derivative, then you definitely have a second derivative, right? And now things start to get pretty ugly, all right? Check this out. If you have fx and then x, that means you take the partial with respect to x first, right? And then you do it again. Or you could do fxx or f11 or partial with respect to x of partial of f with respect to x. Or you do partial squared f over partial x squared. Oh my God, this is giving me a headache, right? Here's the partial with respect to y, partial with respect to y. Okay? This one is important, all right? Look at this one right here. If you see someone write down, the second one is the one you'll see most often, fxy. That means you take the partial with respect to what first? X first, then y. You can see it right here in this notation. Do the partial with respect to x first, then the partial with respect to y. So you're reading it from left to right. Here, you do which one first? Y then f. What do you think the 1, 2 means? 1 is the first variable, 2 is the second. So we say x is the first variable, 2 is the y is the second one. This one over here, f, you do the y first, then the 1. So 1 is the x. All this fun stuff. All right, let's see if we can't proceed now. Probably Newton or Leibniz. Let's see here. This one. Find all second partial derivatives of this. Second partial means you're going to take two derivatives. Partials means you're going to hold one variable constant, the other not. What's even possible? What's even possible? We can have f xx, we can have f yy, we can have f xy, we can have f yx. Right? That's everything that's possible. So let's start with fxx. So first thing I'm going to do is well, I should do it this way. I'm going to do this by first figuring out what partial with respect to x is of it. What is that? What's the partial of that with respect to x? 2x plus 0, I'm not going to write it, minus 30 x squared y squared. Okay, good. That's right. Now what I need to do is I need to take the partial of that with respect to x again, which would give me what? 2 minus 60 xy squared. That's it. That's the first one. From which one? Uh-huh. Did you say fyx or fxy? You can do fxy. underneath this? Yeah, to get fxy, this one, you need fx first, which we have, yes. Okay, but I'm just going to write it down like this. Let me do fyy. Well, first thing I need is fy, right? Partial of f with respect to y is? Partial of f with respect to y. 20y to the 4th minus 20 x cubed y. What's the partial of f with respect to y again? 80 y to the 3rd minus just 20x cubed, yeah. Because you're holding the y is your variable and the 20x cubed is your constant. Got that. Now, I'll do this over here. Let's do fxy. That means we need to take this one, right? That's fx. And now we need to do the partial of that with respect to y. So what's the partial of that with respect to y? Well, derivative of 2x with respect to y is what? 0. And over here, the only thing I have to look at is y squared. What's the derivative of y squared? 2y, but then all that other junk, right? So what is it? Negative 60 x squared y. What's fyx? So this time I'm going to take this one, and I'm going to take the derivative of that one with respect to what? X. What's the derivative of 20y to the 4th? 0. Over here, all I have to worry is that x. Derivative of x cubed is 3x squared. Everything else is a constant. So negative 60. Those are the same. fxy and fyx are the same. Coincidence? We shall see. It's going to be very important later. But I want to point it out at least. You do see that those two are the same? Your partials are the same. Your second partials, fxy and fyx, are the same, right? fxx and fyy are not the same. Right? These two weren't the same, but those two were. We'll see what that means to us later. It's going to be a very nice thing when that happens. We'll have what will be called later a conservative vector field, and that will allow us to do nice things. But that's later. Well, when you do second partials, those are the only possible ones, right? If you take two letters, x and y, there's only 4 different ways you can arrange them, like, xx, yy, xy, yx. That's it. Okay, given this, this is a nice theorem, Clairaut's theorem. It says, if you have a function of 2 variables, if f is defined on a disk that contains the point x0, y0, and fxy and fyx are both continuous, then they're the same. We will refer back to this later. Okay, just for now, be aware if I mention later Clairaut's theorem, I'm talking about this. Oh, crap. Now, in the last one, we did the second partials, right? But there is no limit as to how many partials we can take, right? I don't have to stop at 2. I can say take the partial with respect to x, now y, now x, now x again, now y. I mean, I could, right? You could theoretically do that. So let's see what this one does. This one means we're going to do what first? Partial with respect to what first? X. Now, I'm working with that first x right there. That's the one I'm working with first. first. So what is the partial of that with respect to x? To x, right? Minus 0, okay, so minus 30 x squared y squared. Now what am I supposed to do? Respect to y. So fxy would be 0 on the first one. What about the next one? Treating your y like the variable. Negative 60 x squared y, right? What's the partial now? Again, we do y again, don't we? So fxyy would be the partial of that with respect to y, which is negative 60x squared. And now we do the final fxyx. So partial of that with respect to x, negative 120x. And that is all she wrote there. Nothing. That we can do fourth partials if we want. Yeah. I mean, right now we don't have a meaning to this. All this does is exercise your brain a little bit when you're holding things constant and the other one's not, and just keeps track of things. Let's try the other one. I'll try and do it on the same page here. The other one I need to start with what? Fy first, f with respect to y, which would give me 20y to the fourth minus 20x cubed y. Oh, by the way, the TI-89s do partial derivatives. I don't think so. Okay, now fyxx or fyx is a partial of f with respect to y followed by with respect to x. So follow that answer we have up there with respect to x, and what would you get? Minus 60x squared y. And then follow that up with x again. That's what we want. Negative 120 xy. Pretty close to the other one, but they're not the same. Yeah, it was only 3. So, all right, that's just exercise in partials. Now, maybe some of you have heard of things called Laplace equations. Physics, mechanics, circuits class, Laplace, come up a lot. Okay, a Laplace equation is any equation that satisfies this right here. So functions would satisfy these are called Laplace equations. They're used in mechanics, heat dynamics, fluid flow, electric potential problems. So let's just see what the hell a Laplace is, what a Laplace equation is. First of all, you're given a function of two variables. Now, I've been giving you f of xy, right? But now I'm going to call it u of xy instead. Then this first one, or sorry, the second equation over here says, and these are the same, just two different ways of saying the same thing. The second one says that if you take that function, you take the partial with respect to x, followed by the partial with respect to x, add it to the partial with respect to y, followed by the partial with respect to y. If those two add up to be 0, then the equation you start with, right, it's right here, or sorry, this equation right here is called the Laplace equation. So let's see if we can use that. To determine if u is a solution to the Laplace equation. So there's a function of two variables, right? Is that a solution to the Laplace equation, or does that function satisfy the Laplace equation? So here's what I want to check. I want to check that uxx plus uyy equals 0. Is it true or not? So what's ux? What's ux? 3x squared plus 3y squared. What's uxx? 6x. That's all. Agreed? What is now, I'm checking uy. What's uy? 6x y. And what's uyy? 6x. Right? So now let's check it. Does uxx plus uyy equal 0? Well, does 6x plus 6x equal 0? Only if x is 0, right? No. So it does not. It is not a solution to the Laplace equation, because that does not equal 0. Now, had it been 6x and negative 6x, now then it would have satisfied the Laplace equation. All right? Implicit differentiation. Y'all remember? Do y'all remember implicit differentiation? Been a while. Let's try and do a quick little recap of implicit differentiation, just in case it's been a while. Let me just start a new one here. Okay, back in Cal 1. If you had something like this, xy squared plus x squared y equals 10xy, and you were asked to find dy dx, that was the same as finding y prime. Well, one thing you would like to do is try and solve it for y. But if you cannot solve it for y, then you had to use implicit differentiation. So the way you would do it is you would look at the equation, and at least in my classes what I would do is I would draw a little squiggly line to let everyone know I'm about to do implicit differentiation. I would just differentiate everything I see with respect to x, meaning, treating x like my independent variable. So let's take a look at the first differentiation. I'm going to try and take derivative of xy squared. All right? Now I am not holding x constant or y constant here. This is not a partial derivative. What I'm doing is I'm saying that y depends on x. So I have to apply product rule here. What is the derivative of a product of x and y? Right down the middle here. What's the derivative of that product? Well, derivative of the first one, which would be, what's the derivative of x? 1, because it's with respect to x, right? That's why I highlighted it yellow. It's 1 times y squared plus, now the derivative of y squared. 2y, y prime, or your teacher might have written, instead of y prime, dy dx. But that's chain rule. The derivative of something squared is the 2 comes down, right? Then the something, and then derivative of the something next. Here, in this case, derivative of y is y prime. Why didn't that happen over there on the x? Because the derivative of x is 1, because it's with respect to x. Does this ring a bell, implicit? Then I'm done with product rule plus, oh yeah, I didn't put my x. Plus, now product rule on the second one. Derivative of x squared, just 2x, and then y. Plus derivative of y prime times x squared. So there's your product rule there. Equals the other side, product rule. I'm going to do product rule right down here. What's derivative of 10x? 10, then times y, plus derivative of y prime times 10x. And then what you would do is you would get all your y primes on one side, everything that didn't have y prime on the other side. You'd factor out y prime and divide through. Does that ring a bell? That's right, because I'm taking derivative of y squared, right? The derivative of y squared with respect to x is first the power rule. 2 comes out, 2y. But now you got to go in and take derivative of y. Derivative of y is y prime. That's the big part of implicit you have to be careful with. Okay, that's the way we did it back in Cal 1. Now let's go back to ours. Let me take a screenshot of that for you here. Where'd it go? I lost it. Come back. Guess it doesn't want to. It wants me to stop, I guess. There it is. Okay. So let's take a look at this. Let's try to do implicit differentiation on this. What do you notice about this that's different than it's got a z in it, right? Now we have x, y, and z. Before, we said find dy dx in the previous problem in Cal 1. Said dy dx because we said y depends on x. So we just want to know how y changes with respect to x. Here, z is assumed to depend on both x and y. And so the only way you can know how z changes with respect to x is if you hold your y constant. Okay, let's try this first. I'm going to try the derivative of x cubed with respect to what variable? X. What's the derivative of x cubed with respect to x? 3x squared? Right? Okay. Plus, now what's the derivative of y cubed with respect to x? What do you think? If we're taking a partial, aren't we holding y to be constant? Yes? Okay. Let's leave this as a question for now. But everyone here is thinking 0 because partial meant you had to hold one variable constant, right? If you have x and y, you got to hold one constant. Okay, so I'm going to leave this as 0 as a question. Let's just leave it open to you to just think about. What would the next piece be? What's the derivative of z cubed? 3z squared times the derivative of z itself, right? With respect to what variable? X. Now, I'm not going to call it z prime. I'm going to call it partial z with respect to x. Okay, that's the z cubed. Yes? Well, prime is usually reserved for Cal 1 when you only have 2 variables. When you have 3, then, when you just say z prime, did you mean derivative of z with respect to x or y? So you need to clarify that with that x down in the bottom. Okay, plus, now what? Oh, wow. How do you do derivative of 6xyz? Product rule, but look, I only have to look at it as a product rule right there. What's 6xy? Well, I'm treating y like a constant, right? So that's really like the derivative of x with 6y sitting in front of it. So that should just be what? 6y. But it's a product rule, so I'll have 6y what? Times z plus, now you do derivative of z and then times the other one. Does that kind of make sense? Holding your y constant. The derivative of this side right here is going to be 6, what did y'all say? Y. That's derivative of the first one, times the second one, which is z, plus now derivative of the second one, which is partial z with respect to x times 6xy. That's your product rule on that 6xyz. And that must equal what? 0, the other side. Well, we said that it would be 0 if we held y constant, right? And that's the thing. You have to hold y constant if you're going to be doing it with respect to x because you've got two variables. So z is actually some function of x and y. That's what we're assuming here. So it's like some surface. And so in order for us to figure out a derivative, we have to hold one of them constant. So if you're going to do this, you got to hold your y constant, which means the derivative of it by itself is 0. So the answer to this question is yes, that is true. Yes. Now, what would we still need to do if we were trying to answer this? Yeah, you'd need to take all your dz, dt's, or partial z with respect to t, take those two terms, get them on one side of the equation, take everything to the other side, factor out, divide through. I'll let you, that's an algebra exercise, I'll let you do that on your own. How would this problem change if we did part B? So let me take a quick snapshot and, yeah, we treat x like the constant now, right? So here's how we get it. What's the derivative of x cubed with respect to y? 0. Okay, plus what's derivative of y cubed with respect to y? 3y squared. Then plus, now we're going to do the same thing, derivative of 6xyz, but we're going to do treating our, oh, I missed z cubed, thank you. Forgot that one. Z cubed was what? 3z squared partial z respect to y. Now our product rule. Treating x like a constant, what's derivative of 6xy? Treating x like constant. Just 6x? So 6xz. And then plus, now derivative of z is partial z with respect to y. And then times 6xy equals 0. You would solve for partial z with respect to y the same way. Isolate it, move things over, right? Factor, divide. That seem okay to you? You could, yes, because you could do it, you could hold more than one constant, yes. So it's similar sort of thing. And we're actually going to talk about more derivative stuff in 11.5. We're going to actually have something called the chain rule for higher order functions, and we'll spend a lot of time talking about it actually. All right, have I finished? I actually think I might be done with this section. Am I really? Yeah. Let me take a quick snap of this. See? All right. This doesn't happen often, but have a good day. Huh? I think we're right on track, right? Well, actually, we're supposed to. Hey, y'all want to do a quiz? No, y'all want to do a quiz? We're supposed to. Wednesday we're supposed to finish 11.3. So we're going to be a little ahead, which is good because we need some time for 11.4, 11.5 to finish off everything before that exam. But you have a lot of homework, so I'll let you go early so you can go start your homework early. Because I know that's what you're doing right now. Okay, let me turn this off.